In the previous class, we were looking at how to get different kinds of uncertainties from neural network. We looked at both aleatoric and epistemic uncertainty. Can someone tell us how we were finding out the aleatoric uncertainty in neural networks? What were we doing to get that? Okay, Rishabh, what were we doing to get the aleatoric uncertainty in a neural network? Can you be a little louder? Okay, so we said that we can put a noise model. We could put the noise model to be homoscedastic noise or heteroscedastic noise. In the case of homoscedastic noise, we could make it homoscedastic non-learnable, homoscedastic learnable, or heteroscedastic, which inherently is learnable. In the heteroscedastic case, we said that we are learning both mu and sigma as a function of x. But importantly, the uncertainty that we are getting is still coming through a distribution. We still say that our y is normal with a certain mu and a certain sigma, right? So we have this kind of uncertainty that we're putting is distribution based uncertainty. We had to put a certain distribution, the normal distribution in this case. We could have chosen a student t distribution or a Laplace distribution or something, but we have to assume the distribution. The second kind of uncertainty that we were looking into was epistemic uncertainty. How are we getting that? Sorry? We can compute the posterior over the parameters theta given the data, but that is very hard to find in the closed form for a lot of cases where the likelihood and the prior are non-conjugate. So therefore, we had to resort to what kind of technique? Laplace approximation. If you remember the notebook, we were not doing the Laplace approximation over all the parameters. Instead, we did the Laplace approximation over the last layer of the neural network. Right? So that gives us the posterior P of theta given d. Rather, it gives us an approximation to the posterior P of theta given d as some q of theta, some probability density function in theta. And just we'll figure that out. So we can get the epistemic uncertainty via putting a prior over the parameters theta and then obtaining a posterior over them. We can then approximate the posterior with normal distribution, which is known as the Laplace approximation. After that, how do we get the uncertainty after putting the Laplace approximation? So what are we trying to find the uncertainty over? P of y star given x star and data. So we're trying to find out the uncertainty in our predictions. How do we solve P of y star given x star and data? It's an integration, right? And that integration is intractable. And how do we solve such intractable integrals? Monte Carlo estimation. In a class prior to that, we had started looking into some sampling methods.
I had a doubt in previous class. So when we are taking prior over the parameters in the network, we are also taking prior over the bias.
So that's a good question. You can and you cannot.
Because then if we consider that case which we did in the previous class, like y given by x plus and did something, then like taking a bias over prior. Sorry.
Prior over bias. Yes. So this was one of the things I was also having a discussion with Zeal, with whom we were preparing the notebook. We felt that perhaps it's not needed in many cases. Sometimes you just need a prior over the weights, and sometimes you can put it over. So it's a subjective call. The other subjectivity to this question is where do you put the, what kind of weights do you want to consider? Right? Do you want to consider all the weights in the network for which you want to put a prior over or have them as stochastic? Do you want them only over the last layer, or can you have it over a subnetwork? And the subnetwork will turn out to be optimal in various ways. Okay, so we have already looked at some sampling methods. We'll quickly revise them to get back the context before we go on to the topic for today, which is rejection sampling. So we've looked into Monte Carlo simulation. We said that the general form is integral fx px dx. By this time, I think all of us should be having this on a fingertips. Integration fx px dx is given as 1 over n summation fxi, where xi is drawn from px. We estimated the value of pi using this. We said that we can use this to estimate the prior predictive distribution. We can similarly find out the posterior predictive distribution this way. And we can also estimate the marginal likelihood, which we discussed, that it's the denominator term in the Bayes rule. So which is P of y given x, or P of data generally. We do that as the integration of these two terms, P of y given x and theta and the prior. And we were able to obtain this. And we said that we could instead use the Monte Carlo methods, because we know all the terms. We know P of theta and we know some f of theta, which is P of y given x. When we were trying to do this, we said that we might need to work with log probabilities. So we converted that integral into, transform that and looked at the log of the integral. And we ended up with the log sum exponential trick, which we solved via the code. And we were able to show that the values we were able to get were fairly similar. We also said that the estimator which is coming through the Monte Carlo estimator is an unbiased estimator, but it has variance which converges very slowly. So therefore, sampling can be very inefficient for various kinds of tasks. It's often better to use analytical methods if you can. We also looked at sampling from some common probability distributions. We said that the main distribution you want to start off with is the uniform distribution. Once you have uniform, you can get various other distributions. For uniform, we said that let's look at this linear congruential generator, which is a PRNG algorithm, pseudo random number generation algorithm. The main thing to remember here is this cyclical diagrams, this clock-like diagrams. We can start with the seed with certain values of a, m, c, and we'll get numbers in the range from 0 through m minus 1. And if we divide that by m, we'll get numbers in the range of 0 to 1. We looked at this, then we said that if we can sample from uniform between 0 and 1, we can also easily sample from uniform between a and b using simple. Okay. So Utkarsh is asking the question he asked 2 classes back. Do we have any proof of that we are able to go through all of these values? And last time I said that I do not know. I checked around with other faculty and they also said that the proof does not exist. It's not a trivial to show. Like what we saw was empirical evidence where we looked at the density functions. Sorry, we looked at the empirical density and it turned out to be similar to uniform distribution. Right? The other thing we have to play around with is the fact that we have M, A, C, and we need to have a careful consideration of these, right? So that we are able to, so like if you look at the second example, for these values of M, A, and C, it's not a uniform generator, see, right? It is not picking up the different values. It's only picking 3 values and it will cycle through them, right? But if you have carefully chosen, it turns out to give you something which can reasonably well pick up all the numbers in the range. Right? That's what we're trying to do. We can sample from uniform 0, 1, and therefore we can sample from uniform A to B. We also looked at inverse CDF sampling, where the idea is that we will start with the PDF of an expression, we'll then accordingly get the CDF for that particular distribution. And we'll draw a random number between 0 and 1 from the uniform distribution, and we'll try to get the inverse CDF corresponding to that sample. So we looked at certain proofs for this. There was small calculation mistake in this, but I've now corrected it. This is the key idea. You start with a uniform number between 0 and 1, and you look at the CDF map and you correspondingly figure out the x which would have generated corresponds to that CDF. Therefore, it's known as the inverse CDF method. And if we look at the densities of samples, we will be able to get the density for the corresponding probability density we're trying to get. We then looked at specific examples of normal distribution. Normal 0, 1 we were able to get through an algorithm called Box-Miller. I will just skip the details. Once we have normal 0, 1, we can get normal mu sigma using mu plus sigma times z. And we then also looked at getting distribution, getting samples from multivariate distribution. So first we said that let's generate the samples from normal 0 and where the covariance matrix is identity, mean is 0, covariance matrix identity. And then we need an equivalent of mu plus sigma times z, right? What is that equivalent? So there we had mu plus sigma times z in the univariate case. Sigma is the square root of variance. So similarly, we need something which is the equivalent to the square root of the covariance matrix capital sigma, and we said that that is the Cholesky, comes through the Cholesky decomposition, L into L transpose. Okay. We stopped at this point. So thus far, if you see, our goal has been mainly to start with to have certain predictions like the posterior predictive distribution. Right? This is P of y star given x star comma data, or the prior predictive, which is P of y star given x star. Right? So in order to do that, we end up with typically using Monte Carlo methods, because these are integrations of the form fx dx, fx px dx. These are the integrations of the forms. But here I've mentioned that px is the post, so I'm now using, I've just skipped out theta to make these things simple. So px is the posterior distribution, and this is the integration I equal to fx px dx that we're trying to solve. But typically we don't have px, right? What do we generally have instead of px? So in the case of, so when we're trying to compute the posterior p of theta given d, what can we write it as? Likelihood times prior divided by the normalization constant, which we said is hard to get. So therefore, typically we get the posterior distributions numerator, right? So therefore, we generally don't have p of x, but we have p of x divided by the normalization constant z. That is what is easy to get. That is the joint between the parameters and the data, which is the same thing, if you remember, we use for Laplace approximation. There you find the Hessian of the negative log joint, right, evaluated at theta map. So we can approximate I by the Monte Carlo expansion. So if our goal is to sample from p of x, but we will generally not have p of x, rather we will have something which I will now on what's called p tilde. P tilde is referred to as something which is proportional to p of x, or px equal to p tilde x by z. Right? Again, I want you to concentrate at the form p tilde of x. You can think of this as the likelihood times the prior divided by z, right? And p of x is similar to p of theta given d, the posterior that you're trying to compute. So we'll be looking at a proposal distribution now, right? So what we've said is that p of x is what we want to get samples from, right? But that is hard. The second thing is we don't have access to p of x, we have access to p tilde of x, right? So think of this as p of x can turn out to be a very arbitrarily complex distribution. It's sometimes something of the form of some normal times, some Bernoulli times, something plus something, right? It's not a closed form, easy to sample distribution anyway. If we had the access to the functional form of px, and if it were a standard distribution, then we don't need to study all of these things, right? If px was normal distribution, of px were the uniform distribution, we don't need all these slides, right? But again, remember that we are, okay, let me ask, why are we trying to get samples from px? We want to get the Monte Carlo estimation of integral fx px dx. That is our objective. Typically, we'd be using it for posterior predictive, prior predictive, something like that, or the normalizing constant. So we're trying to obtain those quantities. So therefore, we need samples from Px, but we don't have access to Px. Second, we have access to P tilde of x, and we don't know how to sample from P tilde x. Right? So what do we do? I've given a hint. We will choose Qx, and we'll call it some proposal distribution. We can sample from Q of x because we are proposing it. So let's assume Q of x is a uniform distribution or it's a normal distribution. And we now know how to get samples from uniform, normal, these kinds of simple distributions. Right? So what do we need to now do? What do you think we can do? Laplace. So Laplace approximation gets you the posterior, right? It gives you the posterior distribution. But here we are saying is that I don't care about the distribution, I just want to get samples from that distribution, right? So think of this as Laplace approximation. If all you care about is looking at Monte Carlo estimation for the posterior predictive, right? P of y given x and d, all you care about is that, and you want to solve it via Monte Carlo methods. So then Laplace approximation can be a bit overkill, right? Because first you estimate posterior via distribution, then you generate samples from that approximate posterior, and then you plug them in. So what here we are saying is that can you directly get samples from P tilde of x and plug them in the Monte Carlo simulation, right? So what you're saying is correct. We can approximate P tilde of x with some Q of x, let's say whose functional form we know. In the case of Laplace approximation, it's a normal distribution. But here we're trying to do something else. We just want to get samples from, yes.
Why are we not sampling from P tilde?
Why?
Why are we not sampling from P tilde?
So we can't sample. We don't know P tilde of x. We don't know the functional form. So think of this as it's Bernoulli times some Gaussian distribution. We don't know how to sample from such things. And I'll show you certain examples where this will become clear. But the important thing is, so you should try and remember the context. P tilde of x is P of, you can think of this to be equivalent of P of d given theta into P of theta. For the case of classification, logistic regression, P of d given theta is Bernoulli, right? It has sigmoid terms, and P of theta there is a normal distribution. So it is something you can't compute.
Why don't we directly to leave this approximation from P of x to Q of x?
Yes. So, right. So this is similar to what Vipul was saying. We can approximate P of x with some normal distribution Q of x, and then you can generate samples from that Q of x, and then you can plug in those samples in the Monte Carlo simulation. That is perfectly valid to do. What we're saying here is that why estimate that normal distribution when all you care about is the samples from that. Okay. So can we do something simpler by directly generating samples from P tilde of x using some other method? So what you said is one particular method, and Laplace approximation has certain things which make it not very appropriate for usage in a lot of circumstances. Can anyone tell that?
If it is not a unimodal,
If the P tilde of x or P of x is not unimodal, right? What does Laplace approximation do? It tries to match the peak. It tries to say that it tries to center the proposal distribution at the peak. It can pick up the different peaks depending on how you have initialized, but it can end up very poorly approximating the distribution. Right? Does everyone get this context? Okay.
I have a question. Sir, why can we not get the normalized? We can use Monte Carlo for that.
Yes, you can use the Monte Carlo. So the question is, why can't we get Z via Monte Carlo estimation? And it's a perfectly valid way to do that. And in certain circumstances, we end up calculating that. But in certain algorithms, you don't need to calculate that. So if there is an algorithm which does not require you to get Z, you will always prefer it over an algorithm which requires you to calculate Z. Right? The important thing is that Px is proportional to P tilde of x. Right? So if you were to think of Px and P tilde of x as some functions, right? At places at values of x where Px is high, P tilde of x is also high. and vice versa. So, you want to be using this fact somehow. Was there any other question? Are you giving an answer? Okay, you can try.
So after we are, so the last point says that we can sample from Q of X, which is easy to sample from.
Yes.
So first we sample from it, and then and then what we believe is that some points in, like from Q of X, we can select a subsample of some point that will lie in Q of X.
Okay.
So we can get a criteria such that we can select those points from.
Okay, excellent. I'll want you to stop at this point itself and not give the further details. If you notice, the name of the algorithm is rejection sampling, right? Which means that some of the samples would be accepted, some would be rejected. Right? That is the main idea. Now we have Q of X, which is a proposal distribution from which we know how to sample. Right? Q of X could be normal distribution, uniform distribution. It's easy, trivial for us to calculate some samples. Now we want to be rejecting certain samples and we want to be accepting certain samples, right? And what we're hoping is that the density of the accepted samples is the same as the density of Px, right? That's the broad goal. Reject some samples, accept some samples, and the density of the accepted samples has to be the same as Px. We'll start with that goal and we'll go over the method and then we'll come back and see how this works. So firstly, we'll calculate a constant m such that m is greater than or equal to p tilde of x by qx. For all x, while we write all x, we can't typically evaluate at all x. So we'll have to look at certain discrete evaluations of x, while which we can find m. Right. Then we try and sample from p of x. By sampling from q of x, so generate a sample from q of x, accept that sample with the probability px by mqx, right? So what is the maximum value of px over mqx? 1. What is the minimum value of px over mqx? 0, right? So therefore, you are trying to accept a sample with a probability between 0 and 1. Right? That is clear till now. Let's look at how this may work. So we're given some target distribution p tilde of x. This is p of x over the normalizing constant z. In this case, I've actually chosen it to be a valid density. This is a mixture of Gaussians. If you can see, I have two Gaussians. I have one Gaussian centered at minus 0.5 and one centered at 1. And the left Gaussian has lower variance, the right Gaussian has a higher variance, and they are in some particular ratio that I've had, I think 0.7 and 0.3, something like that, or 0.5 and 0.5. So I have these two Gaussians, but now think of them as some unnormalized density in 1D space that we have, p tilde of x. Our goal is to be able to get samples from p of x, not p tilde. Again, p tilde is not a valid density. We choose a proposal distribution q of x. In this case, I have chosen the normal with mean 0 and some variance. Right. Now, what we want to say is there was some multiplier factor m which we had chosen. Right. What we are trying to say is that let's scale qx by a factor m so that it envelops the p tilde of x. It is always above or on p tilde of x. So I have chosen certain value of m, and as you can see that the distribution qx has been pulled up, right? Because by a factor m. I have chosen it carefully here so that my mqx is always greater than or equal to p tilde of x for all values of x. In this case, I have done it empirically using a very small grid size and evaluating it over all the points. Right. So now we have p tilde q of x and m q of x. I can sample easily from q of x. I know that. I get one particular sample. It turns out to be close to minus 1. At the given sample, I can draw a vertical line, which means now I'm trying to see where it cuts p tilde q and m of qx. So it cuts p tilde of x at one particular value. I've shown that in gray. It cuts m times qx at the dot I'm showing in black, right? And the next thing I said that is you draw a random uniform between 0 and 1, right? So what we said is that you want to be looking at, you want to be accepting a sample with the probability, what was the probability? Px by m times qx, right? Or what we're saying is that you can draw a uniform between 0 and 1 and evaluating u times mqx, right? So if you draw a uniform between 0 and 1 and evaluate u of mqx at the sample x, that comes out to be this value which is shown in this purple color for now, right? Now we will reject this sample. I'm showing rejected samples in red because u mqx is greater than p tilde of x. Q times mqx is greater than p tilde of x, right? So this point is outside of what we would have wanted in the curve, right? But instead, if I had chosen a different sample, so I have picked up now 0 minus 0.2. At this value, if you look at the, you look at mq of x, it's a very large value. You look at a p tilde of x, p tilde of x is greater than u times mqx. U, if you remember, is a number between 0 and 1 from the uniform distribution. So we have seen now two kinds of samples. One was rejected, the first sample was rejected, the second one has been accepted. Now let's repeat the procedure for a lot more number of samples. Right? Here I am showing for 10 different samples. You can see the green dots correspond to the 4 out of the 10 samples which have been accepted. Right? Can you see that all of the accepted samples lie below the curve, below the p tilde x curve? Right? All the samples which have been rejected lie above the p tilde x curve, right? But of course, they will still be below the mqx curve because that's the nature of the algorithm that we are using, right? With 10 samples, we don't get much of a picture here, right? 4 accepted samples. If we were to plot the kernel density estimation plot, KDE plot, based on the 4 accepted samples, then this is the density of the accepted samples shown in green. Doesn't look like a very good approximation to the red p tilde of x that we have. Right? But let's go from 10 samples to 1,000 samples. Right? Now can we see that we have a lot more accepted samples and a lot more rejected samples. Now if we look at the acceptance rates, it is about 0.52. Right? So only 52 in 100 samples are accepted, the remaining 48 are rejected. So it means a lot of samples are getting rejected even for this very trivial problem. Now if we look at the kernel density estimation plot, it looks fairly similar to now p tilde of x or p of x. Actually, it's similar to p of x. Right? But there's still some room. If we go to 10,000 samples, apart from visually looking very cool, it just ends up giving us, so importantly also if you see, we have now a lot of samples which are very, very far. Right? Just because we have sampled a lot more samples from a proposal which is normal distribution, you'll end up getting samples which are very, very far from the mean. And now if we look at the density estimation, it looks fairly similar to the original density which we are trying to get. It's still not perfect. Maybe if you had a lot more samples, it will. Right? Which is again showing you that you can get a fairly good approximation using a small number of samples. But if you want it to be very, very perfect, it will require you a lot of samples because that's the nature of sampling. You end up getting fairly accurate very quickly. Okay, any question till now? So the question is that can we do something better than kernel density estimation? I am not aware of something which we can do because we don't know the functional form of p tilde of x. If we knew that, we could have fit those samples to that functional form and we could have obtained a normal with something. But here we are assuming we don't know anything about it. So therefore we end up kernel density estimation as a non-parametric method to find out the density. Okay. Okay, so I've never thought of, so the question is, can we treat this as a classification problem? Because we can now think of this surface, right? Can you fit some decision boundary, right? So I have never thought of it this way. I don't know if it's feasible or it's done. Like this is the most standard way to do this. You use, so kernel density estimation, think of this as being the continuous version of histograms. So it solves some problems with the histograms, including how to specify the width of the bin or the number of bins, etc. It also has certain hyperparameters like the kernel and the kernel width, etc. But it's like visually you can get a feel of the underlying distribution. I have not thought of this as a classification problem yet. So then you're again, so when you think of this as a classification, you're again trying to enforce a certain structure by let's saying that it's a, let's say, a logistic regression problem. You're trying to fit a logistic regression problem maybe with a different basis function, because just with x and y you'll not be able to get, you'll only be able to get a line, but maybe you have terms like x, x square, x cube, y cube, y cube, y square, y cube, and so on, and then you're trying to get this kind of a surface. The other challenges with using a classifier, again I'm thinking right now, so it could be wrong also, like there is no physical interpretation of going below 0, because the classifier will tell you that you can go below 0, you can go above certain things, right? So the below 0 is not very well specified, and you don't even know what is the behavior outside of the support that you're seeing currently, but could be thought of that. So in the previous slide, yes. This one? Mm-hmm. Uh-huh. So do you want me to explain again? Okay. So let's go back and look at the underlying algorithm first. Right, let's look at the last 3 steps. You have Qx, which is the proposal distribution, which we now know is the normal distribution. In this specific example, we choose an m so that m times Qx is always greater than or equal to p tilde of x. So m times Qx becomes the envelope, right? So till this point, I think it's fairly standard. After that, we want to be able to sample from px, but rather what we do is you generate samples from qx. Right? You generate a sample from qx. You accept a sample with the probability being px over m times qx. And you can do the same thing via code as I've shown, by starting with p, taking a proposal distribution q, scaling the distribution, choosing a sample x from q, and then you are evaluating p tilde of x at that particular sample x. You are evaluating m qx, right? And you can then evaluate u times mqx. So I think this is where the confusion for you is coming in. Like, what is u of mqx doing? No, we can access p tilde of x. So think of this as the likelihood times the prior. If you put in a particular value of theta in the likelihood, you can get that. If you put in that value of theta in the prior, you can obtain that expression. What we don't know is p of x. P tilde of x is known to us. So the way we're using u is, so this is equivalent to writing the last line. So accepting a sample with probability px over mqx, right? So let me go with this. Accepting a sample with the probability of px over mqx is the same as if you were to look at mqx and u times mqx and then doing u mqx compared to p tilde of x, right? So let's look at a different way to do this, right? You evaluate px over mqx at any sample generated from qx. This will turn out to be some number between 0 and 1, right? Now, if now you differently choose a uniform distribution and get a number between 0 and 1. Right? If that number between 0 and 1 is less than this number, then you accept the sample. If that number is greater than this number, you reject this. Right? So that's the other way of looking at the same thing. So in this case, we reject as u times mqx is greater than p tilde of x, or p tilde of x over mqx is right is less than u. Right? And similarly, for the other case, we'll accept that sample. If we repeat this multiple times, we'll get the correct density. Yes. So if we know p tilde, we know p tilde to be some, so think of p tilde to be some function which you can evaluate, right? You can evaluate Bernoulli times Bernoulli of something into normal of something. You can put it in a computer, you can get that value, but you don't know how to sample from it. Firstly, p tilde is not a probability density function, so it's not a distribution, right? Secondly, you don't know the normalizing constant also, but it's not something you know how to sample from, right? It's Bernoulli times something. It's a very complicated form. You can evaluate it.
How do we choose the value of m, because it can be anything and we don't know where.
Yeah, just 1 second. Are you clear now?
So I didn't understand the difference between evaluation.
So drawing samples. So let's say that I have. Okay, this is one of the questions we are going to give you in the assignment also. So let's say that I have e to the power minus x square, right? If I give you a value of x, can you calculate e to the power minus x square, right? But e to the power minus x square is also the numerator of the normal distribution, standard normal distribution, which has a certain normalizing constant, root 2 pi, right? Now I don't know that, let's assume for now that I don't know this is the numerator of a normal distribution, right? So I don't know how to sample from this p tilde of x. Right? Given e to the power minus x square, can you tell me how to get samples from e to the power minus x square? No. If I told you that e to the power minus x square is the numerator of a distribution which is known as the normal distribution, and there are methods to get samples from a normal distribution, then you can use that. But p tilde of x you can think of as some function at this point of time, or unnormalized density. Okay, Bhavesh, you had a question?
Like, how do we decide m? Because before that we can also not tell the peak of at which point that p tilde x would be.
So p tilde of x, okay, so let me repeat the question. The question is, how do we get the value of m? Does anyone in the audience want to answer that?
It depends on the distribution. It depends on the proposal distribution and our actual distribution. And like for m, we just have to ensure that at all points the proposal is higher than the actual. And like we could have a very large value and do an overkill, but the best we do have it where it would be sufficiently higher, but and probably touching at some points, but not lower at any.
Okay, so whatever Utkarsh has said is conceptually correct. That is what we'll do. We want to choose an m which is as close as possible to m but forms an envelope. But that's conceptual. I think your question is how to do it practically. Okay, so you are trying to differentiate what p tilde of x? Mhm.
put n in it. But it is not necessary that it will cut at these, but it is still the same maximum.
So I don't know all the details of what you're suggesting. I'm supposing you're trying to suggest that we create another function, right? Which is based on the ratios of these functions, and then you're trying to maximize that. Yeah. Yeah, at this point, I don't know why this might not work, but this is typically not used in practice. Right? In practice, what you end up doing is create a grid of points where you can evaluate p tilde of x and you can evaluate q of x, and then you look at the ratios. That is how you do. Typically, you will not even do this as p of x and q of x. You would do looking at you would solve this by looking at the log probabilities. But your suggestion is an interesting one. So we can think about it later. So now let's see why. Are there other questions? Let's see why rejection sampling works. Right? If you remember, we went and we said that we wanted to show that the samples which we have accepted, or the green samples, they are distributed according to p of x. Now we've forgotten about p tilde. We're writing distributed as per px. Right? The important thing is we have never seen the normalizing constant, but somehow, beautiful in this derivation, we'll be able to account for that. And I'm also acknowledging interesting math channel on YouTube. So what we want to say is that let's generate a sample xs, right? X underscore s is my sample which I've generated from q of s. At this point, I'm actually just saying that the density of an accepted sample is p of xs. And importantly, not p tilde of xs, because that's the normalized density. We know the acceptance probability already as per the method, as per what we have said. We generally call this an alpha of x as a function of alpha of x. The probability that we accept a sample xs generated from q of x, right? The samples are generated from q of x, then we pass it on to alpha function, which is p tilde over m times q. We evaluate it over x of x, right? Importantly, we are now writing it as probability of accepting a sample, right? So we can write this as probability of accept given xs. Right? It's a slightly weird or usage of this base or conditional notation. We have generated xs from q, and then we are seeing what is the probability of it being accepted. Right? The probability of it being accepted is as per the definition of what we've written, p tilde over m times q, evaluated at xs. Right? So this will turn out to be a value. Alpha of xs will be something between 0 and 1. Right? So for every sample xs, we'll have a probability between 0 and 1 of it being accepted or rejected. We can also now write the Bayes rule as follows. Probability that a sample is accepted, right? Sorry, the p of xs given accept, right, is the density of the accepted sample xs, right? And we want to evaluate this left hand side term and show this is the same as p of xs, right? P is the normalized density which we are trying to get samples from. We already know p of accept given xs, right? Given a sample q, given a sample xs generated from q, we know that its probability of being accepted is alpha of xs, which is u over mq. We also know that the p of xs, right, is the density of samples which you draw from q, right? Because we are getting xs from q, so therefore p of xs is just the density of samples which we are drawing from q, which is just q, right? P of accept is the unconditional probability that we'll accept a sample generated from q of x, right? So it's, you can think of p of accept to be the integration or the summation over the numerator for all the samples xs generated from the proposal distribution Q. So we want to be able to calculate this term, P of accept. This is the only term which is going to be slightly hard in this expression. Everything else is easy. Is P of accept given xs times P of xs dxs. This is just the base rule. Sorry, this is just integrating out. But we know that probability of acceptance, we can also now write it as the first term is alpha times xs. Right? The probability that a sample is accepted is what? U divided by mq, right? Which is just the alpha function, alpha of xs. And we know that P of xs is just Q of xs. The probability, the density of samples xs, density of sample xs is just the Q of xs because we have generated the sample from Q. Right. So can you now complete this derivation for me? Sorry? The answer that Utkarsh is giving is 1 over m, or does it involve something else also? There will be a 1 over m term for sure. Is there any other term? Important thing is that we have access to p tilde. Right? We don't have access to p. Anyway, let's work it out in our notebooks and see. All you have to do is to substitute the value of alpha. Alpha is already something in the form of p and q. So just write down the entire expression. You'll start making some progress. Feel free to discuss with the neighbors. It is the first step I want everyone to complete, which is just substitute the value of alpha of xs. Cut out some terms. Get something in the form of p tilde. And remember the relationship between p tilde and p. So p of x equal to what over what? P tilde of x over z. So you want to substitute that value. Right. Is everyone with me till this point? We just write p of accept to be integration of p tilde xs divided by m q xs into q xs dxs. You can cancel out the q xs terms. And now we are left with this integration of p tilde xs dxs, right? Which is, you're saying that you're trying to find out the integration of an anomalized density, which will turn out to be the normalization constant. We don't care about the normalization constant, but we just write in terms of that. P accept equal to z over m. Right, does everyone follow? So P of x equal to P tilde of x over z. That is what you want to be starting off with, and then you can complete this integration. So we now know that P of accept, unconditional probability of acceptance is proportional to 1 over m. Right? Therefore, if you want an efficient rejection sampling routine, what value of m do you want to use? A very large value or a very small value? You want probability of accept to be high, which means you want m to be small. but you want m to be large so that m times q of x is greater than or equal to p of x. So therefore, you have to very carefully choose m. As m increases, probability of acceptance decreases, which means you'll have very few available samples from this routine. A lot of the samples will just get rejected. Okay, so we have p of accept now. We go back to the base rule application. Now we start plugging in values. What is the numerator p of accept given x is equal to? Alpha xs. P of xs is equivalent to q of xs. P of accept we just calculated as to be z over m. So therefore, p of xs given accept will turn out to be p tilde qx divided by n qx into q of xs divided by z over m. You can cut out the q's, you can cut out the m's. P of xs given accept comes out to be p tilde of xs over z, which is our definition of p of x. So we have just shown that the samples that are accepted are distributed as per p of x, which was the original code. So I can quickly show the code which I used to generate the plots. So this is how typically you'll end up. So this is a mixture of Gaussians that I had created as my p tilde. It contains a categorical, so it contains two distributions, and both of them are normal, minus 0.51 and 0.3 and 0.5, and it's a mixture same family. If I plotted this distribution, it looked like the two modes. My proposal distribution was a normal distribution with mean 0, variance 1. I found out the value of m by looking at certain values of xs. So my xs is length space minus 3 to 3. I looked at 100 values. So it's a discrete evaluation. And I looked at the log probabilities and I subtracted them because I wanted the equivalent of which is higher in the prop space. And then I got the corresponding value of m. And then this code was, this is the important code. You generate q as between 0 and 1, and then you look at q into m into q into log prob x into exponential. We have already seen that the probability of acceptance is proportional to 1 over m, right, which is now going to lead to a lot of rejected samples, which makes the entire procedure very inefficient. So that is one shortcoming of this algorithm. The second will come if we do this thought experiment. Let us for now assume that p tilde of x is a normal distribution. Typically, it's in some anomalized density, but let's assume it's a normal distribution in some d-dimensional space. So it's a multivariate normal distribution. And I've chosen a very simple form. Mean is 0, 0 vector, and the covariance is sigma p square times I. So all the values are the same, just sigma p square in this covariance matrix. My q is also multivariate normal with a different sigma, sigma q square I identity matrix, and I've chosen sigma q to be greater than sigma p, right? That is an important thing I've chosen. So maybe this is how my p tilde of x and q of x look like, right? So what I'm saying is that now if I have to find out the multiplier m, because I know everything, I can do this in pen and paper. I don't need to run it through simulation or run it through multiple evaluations. So all I'm saying is that let's match the densities at the peak of p tilde of x and q of x, which is the peak exists at the 0 vector. I've just drawn the 1D realization of this. Think of this as a higher dimensional multivariate normal. Can you do that and tell me the value of m? Can you do this exercise? Match the densities of p tilde of x and q of x at x equal to 0 vector and tell me the value of m in terms of, it has to be some function of sigma p and sigma q. The hint is to just write down the PDF expressions for both of them and put in certain values which I've written here. Okay, let's just look at the expression. We had p tilde of x as 1 over 2 pi raised to power d into sigma p raised to power d. So because we end up putting the determinant term here in the multivariate normal, and then e to the power minus half sigma p square into x transpose x. Right, I've just taken out the covariance inverse and I've put it here because the covariance is just sigma p square I. Right. And similarly, I can write for q of x. Now I'm evaluating them at x equal to 0. So therefore, the exponential term will be e to the power 0, which is 1 for both them. And then what we're saying is that m into q of x has to be greater than or equal to p, right? So which means that m equal to p tilde of x over qx in the limiting case, which turns out to be sigma q to the power d divided by sigma p to the power d, which is sigma q over sigma p to the power d. So that is the mathematical expression, but what do we learn from this? What is the key insight? Why are we doing all of this? So our goal is to have less number of rejections, but we are past the point where we are trying to improve the algorithm. Now we're looking at the shortcomings of the algorithm, rejection sampling. And when I said that the shortcoming is that the probability of acceptance is proportional to 1 over m, or you generally end up choosing m, which is high. That we saw for a simple univariate case. But now what we're trying to do is for a multivariate case, which would generally be the case for many of the problems that we're trying to solve. Yeah. If d becomes large, so I think this is slightly hard to visualize until unless we start putting some numbers. Right? This is also equivalent to how money grows, compounding interest. Can you look at the relationship? What is the relationship between compound interest or compounding money and this equation? Let's say if your money grows at 10% and every year, 10% every year, you start with 1,000 rupees, you don't end up with a lot of money after 1 year. After 2 years, 3 years, 4 years, 15 years, do you end up with good amount of money? Right? So if you look at these ratios, sigma q over sigma p, let's choose very small numbers. So my sigma p is 1, sigma q is 1.1, which is only 10% more, right? Now I'm looking at the dimensionality, capital D, and my value of m which I get. The growth is so rapid, it's exponential growth, that I have to choose the y-axis in my logarithmic scale. I can't show them on a linear scale well enough. So as I increase capital D, capital M goes to 10 to the power 4. Right? Even though sigma p and sigma q are very close to each other. Right? It's only a factor of 1.1, only slight amount of more variance. As a consequence of this, what do you think happens? As m increases rapidly with an increasing dimension, what is the consequence of this? The probability of acceptance goes down, shoots down. For a 100-dimensional problem, it goes down to 10 to the power minus 4. So then do you think a method like this would be useful for solving, let's say trying to solve problems which involve neural networks? We are dealing with only 100. So 100 dimensions corresponds to 100 parameters here. That's what the meaning is. Right? So would it be useful? Acceptance ratios is 10 to the power minus 4. Right? One sample out of 10 to the power 4 samples that you generate out of the proposal queue would be accepted. Right? What is the other problem? So let's say that acceptance ratio is low. Right? Why do we care so much about that? You have to do too much sampling, that is fine. That is evident from this. But where do we use these generated samples in? No, we use for KD plots just to show that the density is similar. But in our machine learning course, where do we use the generated samples? Monte Carlo estimation, right? What is the shortcoming of Monte Carlo estimation? The variance is high. The estimator is unbiased, but the variance is high. So can you see the twofold problem? One, generating samples is very hard. Secondly, you need a lot of samples in Monte Carlo simulation in order to reduce. If you remember the pi example that we saw, we had to generate 10 to the power 8, 10 to the power 9 samples to come to the third or fourth precision, right? So both of these problems going hand in hand makes it clear that rejection sampling like methods are not well suited, right? They're perhaps very well suited for simpler 1 dimension, 2 dimension, like low dimensional problems, but beyond that, it's very hard. What could be some other challenges in rejection sampling like methods? We'll probably have, so numerical underflow we'll have across many of such applications, many such algorithms. But what is the subjective criteria here? All of the things which we are seeing is currently purely numerical, purely objective. What was the subjective decision? Only subjective decision you had to take in this case. Yeah, someone said the answer. Proposal. How do you choose Q of X? Like you could have chosen Q of X to be normal, uniform, studenty, Cauchy, gamma, etc., etc. Right. So this is another of the question in the assignment. We have asked you to look at 3 different proposal distributions and then tell about their acceptance ratios, amongst other things. So how do you choose? It's not a very easy decision to take, especially because the p tilde of x could be highly multimodal. Right? So we still have a few minutes. Let's try and see if we can cover the next topic. Or no? Let's try. The topic is very important. It's called importance sampling. So the main idea, let's come back to the main idea. It is to compute the posterior predictive distribution. Again, generating samples by themselves is not very useful to us, particularly useful to us. We want to be able to compute posterior predictive things based on those samples using Monte Carlo sampling. Right? That we should establish. So we can approximate I by 1 over n times f of xi, where xi is sample, but we do not have access to p, but we rather have access to p tilde of x, which is proportional to p of x. We can approximate I by this, but in rejection sampling, one of the problems was that we were rejecting a lot of samples. right? So think of the workflow again. You use rejection sampling to get samples for P of x, right? You put those samples in the Monte Carlo estimation. Get samples from P of x via rejection sampling, put those samples in the Monte Carlo integration. But the hint is the new method that we are trying to look at. Can we directly solve the Monte Carlo estimation problem without first generating the samples and then putting them in? Right? So it is the previous method was a decoupled method. Step 1, generate samples. Step 2, put those samples and solve the Monte Carlo integration. Right? This is the main intuition. Can we, instead of using the decoupled model, can we look at the coupled method? So what we're saying is that we had to reject samples from Q of x. Can we use all these samples? If we were to look at them in a decoupled way, there is no way. Like we have to accept all this. We have to reject or accept certain samples, right? But that's why this thought-provoking question I'm trying to bring again. Our goal is to estimate this quantity 1 over n summation I equal to 1 to n f of xi. What can we do?
We can assign weight to the sample related to p tilde of x.
Okay, excellent. That is entirely exactly what we'll do. Unfortunately, I forgot to put the pauses, so it looks a bit intimidating. It's not. Let's go over it step by step. So we had this integration problem of, we were trying to solve this problem of I equal to fx px dx. I can write this as integration of fx px divided by qx into qx. So I divide and multiply by some qx, right? So the main problem in this equation that we're seeing is that we don't know how to sample from px or we don't have access to px. In this case, let's assume that we don't know how to sample from px for now, but we know how to sample from qx because that's the proposal, right? Now what we're saying is that let's look at this entire thing as some f dash of x, right? The form of Monte Carlo integration is some function x into some probability distribution from which we know how to sample. So through some very simple manipulation, what we're saying is that we can write I equal to fx wx into qx, where wx is px over qx and it's called the importance weight. That's all we needed to do. Now in this method, are we rejecting any samples? No. Generate a sample from qx, evaluate w of x, evaluate f of x, and just multiply fx into qx into wx. Sum them up divided by the number of samples that you have generated. Right? So we can then write I equal to the expectation of fx into wx, which we can now think of as a new function f dash of x, but it's the same functional form, integration of f dash x px dx or f dash x qx dx. Right? So what we're saying is that integration fx px dx is the same as integration fx wx qx. So px has been replaced by qx and fx has been replaced by fx into wx. Everything else is just simple manipulation. Like I want to again ensure that everyone understands the coupling and the decoupling we were discussing. In the previous case, when we were discussing rejection sampling, we said that it's a two-phased method. First, you get samples from px by getting samples from qx. Whatever samples you get, you then plug them into your Monte Carlo estimation, right? So you waste a lot of samples in the first step itself. Importance sampling is, importantly, it's not a sampling technique, if you noticed. It's just a smarter way to do Monte Carlo integration, right? Rejection sampling was a sampling method. You're trying to get samples from something. Here, you're not trying to get samples. You're trying to solve the main problem at hand, which is the integration. So then we can write integration fx px dx to be equivalent to be integration fx wx qx, and qx we know how to sample from. Yes.
Why is it called why is wx called the
Wx calls the importance because, let me show you an example and then it should become clear. So I'm now trying to solve a problem where I have, this is my Px, it's the same mixture of Gaussians that I've been using. I have created an fx which is 10 minus x square over 20. So if I plot my Px and fx, they look like the following, right? I have chosen a proposal distribution Q to be a normal distribution, mean 0, variance 1, and now plotted all the things at hand, Px, fx and qx, right? Now I can get a sample from Q, right? Q is a distribution, normal distribution, I know how to get sample from it. I have also defined a function which finds out the w. For any given x, it finds out w of x. So it's the Px divided by Qx. That is the definition of Q. And then I'm plotting all the things. So let's see this. It's showing the check mark corresponds to a sample I've generated from Q of x, right? I correspondingly draw a line above. I know the sample x is minus 0.9. I know f of x I can evaluate. I know the functional form of f. I know q of x, like q is a distribution, so I can evaluate q of x. I evaluate w of x as px over qx. That comes out to be 1.028. Right? Here can you see the w is almost 1. Right? And fx into wx I can calculate. Turns out to be 0.473. So this was the case 1 where px and qx are comparable and high. Right? Both the value of px and qx are high if you see. So 0.266, reasonably high. Let's look at the second case. Px is low and qx is high. So if we were considering a rejection sampling like scheme, we would have rejected this sample. Right? Px is high, px is low, but qx is high. So this is particularly the region. If you see, px is high, sorry, px is low, px is this red, and the qx is high. In rejection sampling, we would have rejected this, right? So in this case, the weight comes out to be 0.02. Do you think this is now matching your intuition? This is perhaps not a very important point sample. It should deserve a less of a weight, because this is at the point where the proposal says that the proposal will generate points at this because q of x is high, but the p of x is low at this point. So the density which we are concerned with is very low. So therefore, all such points should be getting a very low weight when we are trying to compute the integration. Case 3, px is high, qx is low. Right? What does this correspond to? What do you think? What point might it correspond to? Px is high, qx is low. So I have said minus 0.5. Px is high, qx is low. So what you're saying is also perhaps correct. If you look at minus 0.5, right? So px is high, qx is low, which means that there is a very low probability that qx would be able to generate such samples because qx is low, but p of x is very high at those points. So therefore, we should be giving a very high weightage to such points. They are hard for qx to generate, q to generate such points, but they are the points where the density of p is very high. So therefore, we should end up giving a lot of weight to these set of points. And that you can notice is w of x turns out to be 1.901. So the weight of such points turns out to be high. Final case, px is low, qx is low, we'll get up some weight. Right? The two important cases I think are this one, px is high, qx is low. Again, if I repeat, qx is low means that it is a very rare event. It's a rare that q distribution would be able to generate such a sample. But p, the probability density according to distribution p at this point x is very high, which means that this is an important sample. Right? And it's also more important in the context of Q not being able to generate such samples easily. Therefore, the weightage of such samples should be high. If we looked at the case before this, Px is low means that this sample is perhaps not too important. But if Qx was also low, it would have still been okay. But Qx is very high. It means that Q has a very high tendency to generate samples in this region, right? But those samples are not useful because Px is low at that point. Therefore, the weight that you'll end up getting is very close to 0. Right? So, is that answering your question? So, it may take a bit of more time and running through this notebook to get it even better solidified. If we come back, we'll end this topic. May take 1 or 2 more minutes. I did a bit of cheating here. What was that? I used P, but we never know P. We know P tilde. So this is where we come. I think one of you asked this at the start of the lecture. So our integration is fx px dx. We only know P tilde of x. So I write P of x to be P tilde of x over z. I can write that. And then I'm trying to compute this quantity of interest. And now importantly, I need to estimate z. That I can estimate via again a substitution. Right? I can write integration P tilde x dx to be P tilde over q into q. And now again I know how to sample from q. Right? So this turns out to be the expectation under the distribution q of P tilde over q of x. Right? You can calculate that via another Monte Carlo simulation. So therefore, I will turn out to be a function which involves multiple Monte Carlo integrations. There is a nested, you can think of this as a nested integration required. So therefore, you will get it as some f of x into some w tilde of x. Right. So the mathematics of this is perhaps a little boring, but the essential idea is that you can compute z and then you can plug that in. Okay, we are out of time. I'll end there. Any final questions? Okay. So in terms of logistics,